So Newton was not the first to discover gravity. He discovered that gravity is universal. This is probably a myth done later in life. Probably never really actually happened, but the legend states that Newton was sitting under an apple tree, realizing that the Earth's pull on the apple also extends to the pull of the moon. So Newton discovered that gravity was universal. What does that mean? Well, in Aristotle's time, before Newton, motion of the planets and stars were considered natural and were not governed by the same laws as the objects of Earth. So before Newton, they thought there exist different laws. There was laws for celestial objects, things in the sky, and there were laws for terrestrial objects, things on the ground. And they didn't know that these two things were the same, that everything goes under the same laws of physics. Newton recognized that a force directed to the sun must act on planets. He recognized that the gravity on Earth is the same gravity that's pulling on the moon, and it's the same gravity that the sun is pulling on the planet. So that gravity is universal to all objects. This is similar to the force that Earth exerts on an apple that falls. This synthesis, and synthesis just means the proper definition of synthesis. Synthesis means the combination of ideas to form a theory. So he combined the ideas that the same set of laws apply both to celestial objects and terrestrial objects. And he came up with the idea of the law of universal gravitation. Everything pulls on everything else. Every body attracts every other body with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance separating them. So he came up with the idea that even a small apple pulls on everything in the universe. How much it pulls depends on its mass and the mass of the other object and the distance separating them squared. So this entire statement can be written in that little curly thing after force means proportional to. So written in mathematics, force is proportional to mass of one object times mass of another object divided by the distance squared. Or written using variables, F is proportional to m1, m2 over d squared. So the greater the masses m1 and m2 are, of the two bodies, the greater the force of the attraction between them. The greater the distance of separation, the weaker the force of attraction. Here's a question. Which pulls more strongly? Which has a greater force? The Earth's gravitational pull on the moon, or the moon's gravitational pull on the Earth? There you go. Remember Newton's third law of motion. For every action, there's an equal, keyword equal, and opposite reaction. So if the Earth pulls on the moon, there should be an equal and opposite pull, and that is the moon's pull on the Earth. They will be the exact same in magnitude, just opposite in direction. So what was Newton's most celebrated synthesis? So synthesis is the combining of ideas. This would be of earthly and heavenly laws. Remember, earthly is terrestrial, heavenly is celestial. So this synthesis provided hope that other natural phenomena and followed universal laws and ushered in the Age of Enlightenment. So gravity is the weakest of the four known fundamental forces. With gravitational constant, so when you say two things are proportional to each other, that means that usually there's a proportionality constant. So if, for example, one thing was proportional to another, it could just be twice as big. So if another force is always twice as much, then they are proportional to each other with a factor of 2. The proportionality constant for force and the two masses and distance that we call gravitational constant, the capital G. This universal gravitational constant is equal to 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Once this value was calculated, they were able to then calculate the mass of the Earth based on it. So what is this? What is this constant more closely related to out of these four? So looking at the equation, F equals G times M1 M2 over D squared. This universal gravitational constant G, which links force to mass and distance, is most similar to which of the following? And lowercase g is acceleration due to gravity. Would it? Isn't B also acceleration due to gravity? So if you have two answer choices that are the exact thing, it can't be both B and C at the same time, can it? They're the same. Because it's the answer. Pi is a constant that simply relates the circumference of a circle to its diameter. G is a constant that relates the force of a mass to its and its distance. So if you go over to this diagram and get G by itself, G would be thus equal to force times distance squared over the product of the masses. So it relates force, mass, and distance, and it never changes. Constant. Pi is just another constant that appears that relates the circumference of a circle to its diameter. So it's out of all of these, it's more closer to being like pi than it is to actually having to do with gravity and acceleration. It's just a relationship. So the inverse square law relates the intensity of an effect to the inverse square of the distance from the cause. So intensity is proportional to 1 over distance squared. Whenever you have 1 over distance squared, this is known as an inverse square law. Whenever you have 1 over something squared, it's an inverse square law. And what this means is as you increase distance, the amount force is going to also decrease, but it's going to decrease at a faster rate. So even at great distances, force approaches but never reaches 0. So you are currently pulling everything in the entire universe with a non-zero force. So here's an example of an inverse square law. So you have a can of paint, and if you were to spray it at something that is 1 unit of distance away, it'll cover like 1 layer thick. But if you were to double your distance, the amount of paint, the layer that you can spray on it, would go down by 1/2 squared, or 1/4. If you were to add another unit of distance, so you're now 3 units of distance away, well, the amount of the thickness of the layer you spray onto that area will go down to 1/3 squared, or 1/9. And if you go 4 units away, this would now be spraying on 1/4 squared, or 1/16. So the amount of the layer, how thick the layer of paint is on the object you're spraying, would go down by the inverse square law. So if we were to start at Earth's surface, the gravitational force on the object would be at some value. But if you go one radius away, it will go down by 1/4. You go 3. So this is an apple. An apple would weigh 1 Newton. At 2 distance units away, it would weigh 1/4 of a Newton. At 1/3, it'd be 1/9. At 4 distance of 4D, which I think is the radius, it would be weigh 1/16. At 5D, it would weigh 1/25 of a Newton. So remember, weight is just gravitational acceleration times the mass. So F equals mg. How far away is the International Space Station? If you had to draw, if you had to put, where would you put it at? 2D, 3D, 4D? Right. 4D? I mean, it's like, you can't even really tell. It's like right here. Yep. So a 1 Newton apple weighs only a tiny, tiny bit less than 1 Newton. So if you weighed 150 pounds up in an International Space Station, you would still weigh 150 pounds. Question is, why are they weightless then? Why are they almost in? Looks like they're floating around in there without any gravity. So the gravitational pull on the surface is about the same gravitational pull as on the International Space Station. Why does it appear like they're in no gravity? There is gravity is only 10% less up there, I think. So something that weighed 200 pounds would weigh 180, I think. Or maybe I could be wrong. I think it's, I don't know. It might be only like 1 or 2%. Forget. I have to look up there in a second. It's they're like almost on the surface compared to the size of the Earth. What happens if you were to jump off of a building? On your way down, what would it feel like? Have you ever went bungee jumping or jumped on a trampoline? um, So the force of gravity between two planets depends on our what? So it depends on our atmospheres? Yes. So looking at the equation only has mass and distance in it. And a constant, but you don't include the constant. If the masses of two planets are equal, are each somehow doubled, the force of the gravitational between them would be what? So F equals G M1 M2 over R squared. I like answering these questions by replacing everything with a 1. Or a box, I should say. Constants get a 1. So if you don't change something, put it as a 1. And it's saying that you're doubling the two masses. So what is 2 times 2? 4. So that means that the force, if you double the masses, should quadruple. So note that both masses are being doubled. So a double times a double is a quadruple. If the mass of one planet is somehow doubled, the force of the gravity between it and the neighboring planet will be what? Yes. So you're only doing one of the masses are doubled. And so if you just double one, it's the same thing as multiplying both sides by 2. What would happen if you doubled the distance? What would happen to force? So G isn't changing? Yeah. So you're doubling the radius. That's 1 over 2 squared, which is 1/4. So the force will be 1/4. And if I had said what would happen if you half the distance? So G stays the same, the masses stay the same, and this becomes a half. So that'd be 1 over a half squared. That'd be 1 over 1/4. So 1 squared is 1, 2 squared is 4. Dividing by a fraction is the same thing as multiplying by the reciprocal. So 4 times. So if you half the distance, the force will increase by a factor of 4. Weight is force an object exerts against a supporting surface. So you only really experience weight whenever you are resisting motion. So standing on a floor, you experience your weight. Weight is caused by the force of gravity, but you only notice it whenever you're pushing against the floor. So standing on a scale in an elevator, accelerating down, less compression in the scale causes springs. So if the elevator is going down, so you're at the top floor and going down, you actually feel less weight. You'll feel lighter. If the elevator is shooting upward, you put some rockets on it, your weight will feel greater, and it feels like you're being pushed down into the ground more. So as it's accelerating upward against gravity, the compression and springs will be greater, and so you have a greater weight. If you're moving at constant speed in the elevator, that's the same thing as if you're standing still on the ground. Because remember, force has to only deal with acceleration. So if you're not accelerating, meaning your velocity is not changing, you would have the same weight. So weightlessness is when there's no supporting force, such as in a free fall. So if you were constantly falling, you would feel weightlessness. You would feel as if you have no weight. You're not pushing on anything. Now, technically, there's air resistance pushing you up. You would eventually start feeling air resistance. But in a vacuum, you would feel completely weightless. Astronauts in orbit are without support structures and are constantly continual state of weightlessness. So they have the same gravity up there almost, but what they're doing technically is they're falling down to Earth. So the International Space Station, I'll draw it not to scale. They are falling down to Earth, but they're also moving at crazy high speed this way. Or I should say this way. They're moving at crazy high speed this way. So as they move in this direction, they're also being pulled down to the center of Earth, so they get right here. And they're moving crazy fast this way while being pulled downward. And so as they start trying to move in this direction, Earth pulls them down, and the same thing keeps happening. They're trying to move really fast this way, Earth is pulling them very far this way, and what happens is that their speed that they're moving forward and the speed at which they're falling down to the ground match. And they constantly move in a circle around the Earth in orbit. So they're constantly in free fall. They're constantly falling back down to the ground, or they're just going so fast they miss it. You could think of it like this. Let's say that you have a golf ball, and you go and hit it. So go draw a parabola and hit the ground. Now if you hit it harder, go draw another parabola and go back and hit the ground. So it's constantly falling back down to the ground due to gravity. But you give it some speed, so it's also going to move sideways. So you hit it really high, and it's going to go a farther distance. And this is assuming you have no air resistance. Hit it really, really fast. Eventually go fall back down. But there is a certain speed, in which case it's moving fast enough that it continually misses the ground. It's still being pulled down to the ground, but it's also moving fast enough that it misses. So the astronauts are constantly falling. If you were to jump off of a building, ignoring air resistance, you would feel completely weightless. There would be no way of knowing whether or not you were in outer space, again without air resistance, If floating in outer space versus falling off of a building, you would feel identical to you. That's actually known as the equivalence principle. Einstein's equivalence principle. So if you're standing in an elevator that's not moving, normal weight. If the elevator is moving up, you would feel greater than normal weight. The elevator is accelerating. It has a keyword. It has to be accelerating. If it's accelerating downward, less than normal weight. And if it were to snap, and again ignoring air resistance, you'd feel weightless. Everything inside the elevator will be floating around. There's a plane ride that will allow you to feel weightless. Oh, thanks, Bob. So, what this plane does is it gets up to very high altitude, and then all of a sudden it kills its engine, basically, and starts free falling. During this region of free fall, everybody inside the plane feels weightless. During the climb up, though, you experience almost 2 G's of force, so you weigh twice as much during the ride up. And also during the fall back down, whenever they're trying to pull out of the free fall, you would have felt 2 G's of force. But while in the plane, you can float around for a few seconds. I forget how long the ride is. But it's basically free fall. During the actual thing, though, you have to almost lay flat because 2 G's, you aren't used to it. Where there's a region, and it looks like it's 25 seconds. You get 25 seconds of complete weightlessness. I have no clue how much that plane costs. Our plane ride costs, but imagine it's not that cheap. So when an elevator accelerates upward, your weight rating on a scale would be what? Greater. The support force pressing up on you is greater, so you weigh more. An elevator accelerates downward, your weight would be less. Would you weigh less in an elevator that moves downward at a constant velocity? You would weigh the same. And when the elevator cable breaks and the elevator falls freely, your weight reading would be 0. There's still a downward gravitational force acting on you, but gravity is not felt as weight because there is no support force, so your weight would be 0. If you weigh yourself in an elevator, you weigh more when it does what? Which is the following? Accelerates, not moves. So you would be the same if you're at rest or moving at constant velocity, only acceleration. Do you know about ocean tides? What are ocean tides? Alright, so you know it's the moon causing it. Sun a little bit, mostly the moon. Do you know how? Almost everyone gets it wrong. I think even this PowerPoint gets it wrong. So the differences between ocean levels at different times of the day is called tides. There are typically 2 high tides and 2 low tides in a day. This is caused by the gravitational attraction of the moon. Unequal tugs on the Earth's ocean causes stretching effect which is wrong. That produces pairs of ocean bulges. Because two bulges are on opposite sides, high tides occur for 12 hours. So this is wrong. The number one explanation for tides. So most anywhere, if you Google how tides work, you'll probably get the wrong answer. So again, exaggerating. The wrong explanation is that the water is closer on this side to the moon, and so it's going to bulge outward. And thus we get low tide, because the water is feeding back out into the ocean, like this. This is wrong. Can you imagine why it's wrong? Because the moon is pulling it upward. Because this water in this explanation is being pulled upward. That's not the reason why. So, if you think about it, in this explanation, shouldn't the water look more like this? And we only get one low tide? How are you getting this bulge over here and here at the same time? So, this is the wrong explanation. Let's instead think about the forces. So when you stand under the moon, do you feel a little less weight? No. So the force on the moon is pulling upward isn't that strong. So you would expect very little force. I'm going to exaggerate. So when you're standing over it, very little force. But let's look up here closer to the poles. What's the vector going to look like here? It's going to be slanted toward, I'm exaggerating. It's going to be pointing toward the moon. But what do we know about vectors? So we're going to get a small force downward and a small force to the right. So which do you think has the much greater influence? The pull toward the moon or this downward force? So if we're seeing, again, we have water over here being pushed, and we see, again, this pushing toward the moon. Again, I'm exaggerating. These are all pointing toward the moon. But what we see is the water moves like this. We see that the water is being switched. It's this downward force. If you look at the component, there's a right force and an up force. So what ends up happening is the force, the horizontal forces toward the moon isn't that much. However, you get the squishing effect of where all these downward components are pointing toward the middle, are going to add up and cause the water to be squished outward. That is the better explanation of why the ocean tides exist, and why we see two of them, and not just two bulges instead of one bulge on the side of the moon. And we'll continue tomorrow.